Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I am the director of the Planetarium, and with me tonight are two of the students who work there who also do research at the university. But before we get into all of that, I will let them introduce themselves. So we'll start off with Lindsay.
Hi, I'm Lindsay. I'm a physics graduate student here at UMD.
I'm Eli. I'm a physics undergraduate student at UMD.
So, what people may not realize is not only do the faculty in the physics and astronomy department and other departments at UMD do research, but the grad students and undergraduate students do as well. Both Lindsay and Eli are working with the same faculty advisor who I saw was watching, so hi. To do research on black holes. And I really wanted them to share what they do. One, to kind of show everyone a look at what real astronomy research looks like. Two, because I'm super proud of them and think that what they've done is awesome. And three, it's black holes. Who doesn't like hearing about black holes? So before I fully turn it over to them, as always, if you have any questions throughout the show tonight, leave them down in the comments. I'll keep an eye on it and we'll let these two know when those questions pop up. We'll also have time at the end for questions as well. So without further ado, I think Lindsay is starting us off, so I will turn it over to you two.
Okay, so for our research, Eli and I are working on finding intermediate mass black holes in low mass galaxies. So we're going to break that up a little bit more to kind of start with kind of the basics of black holes and then get into a little bit more about what actually intermediate black holes are, and then low mass galaxies, or why we're looking for them in low mass galaxies. So this first video is going to show you how black holes form, specifically how stellar black holes form. We'll talk more about the different types of black holes after this video, but this is one of the ways that we know black holes form.
Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course.
Okay, so that is how, whoops, stellar mass black holes form. So we're going to start kind of at the bottom of this diagram with the stellar masses. So stellar mass black holes can be about 10 solar masses, and the diameter is about 37 miles across. So with about the diameter of Rhode Island, we squeeze 10 solar masses, so 10 times the mass of our sun, into that diameter of 37 miles. That's why I was saying that these black holes are really, really dense. So on the other extreme, we have supermassive black holes. So in this case, we have 4 million solar masses, or 4 million times the mass of our sun, and in 15 million miles of a diameter. So in other words, that's also 17 suns across. So we have this 17 suns across black hole, but with 4 million solar masses packed into that small diameter. In between that, we have intermediate mass black holes. So obviously those are just the masses and diameters that are between the supermassive black holes and the stellar mass black holes. So we have 10,000 solar masses packed into about 37,000 miles across, or 4.7 Earths across.
We do have a quick question.
Okay.
So the question starts, so Star Trek Voyager lied to me. Black holes wouldn't pull their ship in?
Yeah, so it depends a little bit. So with the solar system, we are in a steady orbit because of our distance from the sun and our velocity going around the sun. And so if the sun were to turn into a black hole, we would still be the same distance and we'd still be going the same velocity. And so we would just continue orbiting happily. But if you are coming in like a spaceship and you get too close into the black hole, then you could get pulled in. But if you're just orbiting it, you're just going to orbit it happily without getting sucked in until something runs into you and then pushes you into the black hole.
And that's where that event horizon comes in. That's that point of no return, right? When you cross that, then you're going to get sucked in no matter what.
Good question. We always get a lot of good questions about black holes. Okay, so this is going to explain how we get black holes of a variety of sizes, but it's going to be specifically looking at those smallest black holes, the stellar mass black holes, and how they can become bigger.
The thing about black holes is they're omnivores. They'll eat anything. Anything that gets close to them, they'll gobble up. One way black holes can grow so large is by eating other black holes. So in a sense, they may be cannibals. A black hole merger is the most violent, the most energetic thing that happens in the universe, period. Picture the scene. 1.3 billion years ago. Two black holes circle each other in a dance of death. The larger black hole pulls the smaller one inwards until they're locked together in a spiral.
Very, very slowly, that orbit is decaying. They're getting closer and closer and closer. And then they will merge into one giant black hole, truly one of the most dramatic events in the universe.
Finally, they collide in one of the largest bangs since the Big Bang. Loved to have been able to safely view the collision of these two black holes up close. Imagine these two black holes as they spiral in toward each other, going faster and faster and faster and faster. And then suddenly, where there appears to be nothing, or just distortions in space in front of you, suddenly there's this enormous burst of energy and everything just rings around you.
Our sun is burning about 100 billion hydrogen bombs every second. And over its 10 billion year lifetime, it will convert less than maybe 1% of the mass of the sun to energy. In 0.2 of a second, 3 times the mass of the sun in matter got converted to energy in that collision.
It was 36 septillion yottawatts. What does that mean? A lot of freaking energy.
That's more energy in that 0.2 of a second than is emitted by all the stars in the visible universe in the same time.
So we know that this collision happens because we've seen that energy that it gets produced when the black holes combine. So after stellar mass black holes, we have our intermediate and then our supermassive black holes. So we know how stellar mass black holes form. That was in the first video. After a star supernovas and then sometimes collapses into a black hole. But we don't necessarily know how intermediate mass black holes or supermassive black holes form. One idea for that is what you just saw in the video, where black holes keep kind of coming together and forming bigger and bigger and bigger black holes. So specifically, Eli and I are actually looking at black holes in galaxies. And we know that every galaxy has, or every massive galaxy has a supermassive black hole at the center. So how did these galaxies get these supermassive black holes at the center? Well, we saw that black holes can combine. And we also know actually that galaxies can combine. And so maybe the black holes in the center of galaxies can combine like the black holes, the stellar mass black holes do. So this is just showing what a galaxy collision might look like. And we actually have some pictures of galaxies colliding. So we know that that happens. So we know that galaxies collide. We have pictures. We also know that black holes collide and merge together because we can see the energy from that collision. So if we are looking at these massive galaxies with the supermassive black holes in them, maybe they came from smaller galaxies that collided together, and those smaller galaxies had smaller black holes in them, and the black holes in those smaller galaxies combined to make the supermassive black hole. And so we are looking for these intermediate mass black holes in lower mass galaxies to see if we can figure out a little bit more to galaxy evolution. So just like how we think that the stellar mass black holes combine and combine and combine to create the intermediate mass and then the supermassive black holes, we think the same thing might be happening with galaxies. So we start with smaller galaxies and then they combine with each other until you get the really big galaxies with the supermassive black holes at the center. So if we can find intermediate mass black holes in these low mass galaxies, then that kind of confirms that idea about how we think galaxies evolved from smaller to bigger. Eli?
Yeah, sure. So the actual details of the research that Lindsay and I are doing depend pretty heavily on how the mass of the black hole at the center of the galaxy affects its structure. So what we see is that galaxies with really, really massive, like supermassive black holes, um, and well, larger supermassive black holes, their spiral arms are very tightly wrapped relative to the center of the galaxy. And galaxies with lower mass central black holes, the arms are much more loosely wrapped relative to the center. So we use a relationship or a number called the spiral arm pitch angle. Lindsay, if you want to go to the next slide, we use what's called the pitch angle, which basically, again, just describes how tight those spiral arms are, or, the distance between them. So spiral arms are much wider. That would correspond to a galaxy with a lower mass black hole. And if they're much closer together and the galaxy is much more tightly wound, corresponds to a much more massive black hole. And like it says there, pitch angle has a direct correspondence to the mass of the central black hole. So the way the project kind of starts, I think there's one more slide, Lindsay, if you want to go to the next one. So there's just an illustration of what I was saying. So galaxies with higher black hole masses, as you can see there, the spiral arms are much more tightly wound, kind of much more compact structure, and with the lower black hole mass, much looser open structure. Yeah, so the next slide. So the way we kind of work with this relationship, it obviously begins with pictures of galaxies. In the data that I collected, and I think the data that Lindsay is using too, we used optical images. So visible light, it's what you'd see if you looked through a telescope. Well, except not as clean because the images were taken by space telescopes. But for the majority of the galaxies that I used, they were taken by space telescopes like Hubble, and then some ground-based telescopes, but a lot of space telescope images. And what you do is you take this raw image of the galaxy, which is the one you're seeing on the left, and you have to kind of edit it a bit to look like you took a picture face on of a galaxy. So the best way to describe it is we don't really get to choose from what angle we take a picture of the galaxy like we can on Earth, because we can't, move to the other side of the galaxy or make it look better for the picture. And so a lot of the times when we take a picture, rather than being like completely face on like my hand is now, so I don't have a better way to describe this, I should grab like a CD or something, rather than getting a picture face on, we get them all at like weird angles that make it really hard to do any analysis on the galaxy. So we have to do something called deprojection, which is basically where you just reverse the effects of whatever perspective you took the image from by stretching and magnifying and rotating the image so it looks like you took a face-on picture of the galaxy. So as you can see here, took galaxy called NGC 1090, deprojected it, and it looks like we got a closer, more face-on image of it after the deprojection or that image editing. So if you want to go to the next slide. For my sample in particular, maybe Lindsay can say the same. I started out with, I think, 77 galaxies that I was going to look at, and I'm sure at least 40 of them got shaved off just because they were at too difficult of an angle to deproject, or it just ended up. The analogy I like to use is, once you stretch and magnify and move an image enough, it just kind of looks like fuzz on a TV screen. And a lot of my images did end up looking like that, so we didn't use them. And that's what you're seeing here. You're just seeing galaxies that are either, don't have a well-defined enough structure to find that pitch angle, or are at too awkward of an angle to edit to be usable. But then, Lindsay, if you want to go to the next slide, the next portion of the project was using a computer program that has a really lengthy name. It's called the Parallelized Two-Dimensional Fast Fourier Transform, which is just a lot of big math words. But it basically, what P2D-FFT does is it treats the galaxy as if it is a perfect spiral, or rather a logarithmic spiral. And there are really easy equations we know to like plot logarithmic spirals. So what it pretty much does is it's almost as if it's plotting logarithmic spirals over that face on, quote unquote, face on image of the galaxy. And it's plotting a bunch of different ones. And then it finds the one that looks like it lines up most with the galaxy. And then it gives you the pitch angle from that number. So a logarithmic spiral does have a pitch angle, and that just again describes how tight it is to the center. So it plots a bunch of these logarithmic spirals over your galaxy, finds which one looks the most like the galaxy, and then reports the pitch angle from that spiral. And that's how we get the pitch angle for the galaxies. Lindsay, if you want to go to the next slide. So what this looks like in data is it reports a pitch angle for every pixel away from the center of the galaxy. And we know we found a good pitch angle, or a reliable number, when you see a steady region in those numbers. So Lindsay, if you can highlight the blue line from pixel, I would say 18 to like 53. That steady line right there tells us that this galaxy is a one-armed spiral, because that is the m=1 mode, so one spiral arm. And it reported a pitch angle of, I would say, probably around 7 to 9 for that range right there. And see, it's just above 0, so we know that this is a reliable number. And when I ran that program on that galaxy, it reported a 6.7 degree pitch angle, so that lines up pretty well. So that lets us know that the pitch angle reported for that galaxy is probably pretty accurate. So if you want to go to the next slide. Once we have that pitch angle, there's already an established equation that tells us the mass of the black hole at the center of that galaxy based on the pitch angle. And I'm not going to read it off, but you can see it on screen there. Pretty straightforward. It's just a number minus a number times the pitch angle, and it makes it pretty easy. So we would use that on the pitch angles reported for all of the galaxies that worked out. And Lindsay, if you want to go to the next slide. That is all of my data right there that you're seeing there. So I had 13 galaxies that reported what looked like good numbers. And of those 13 galaxies, 7 of them reported masses that would be intermediate mass black holes. So that's really good news and really exciting, because we found 7 galaxies that, if the method we used worked well enough, do have intermediate mass black holes. So then we know where to look if we want to learn more about them, or investigate more about these mid-range black holes. So you can see on the rightmost column of both pictures there, if the power of the 10 is between, I believe it's 2 and 5, that is an intermediate mass black hole. So you can see I got a good few of those. So really, really good actually. And 7 out of 13 that worked. That's a pretty good success rate too. So I was really happy with that. And at least for me, that was, oh gosh, about a year and a half in the making. It took quite some time. There was a lot of time slamming my head against a computer desk and trying to figure out how computers work pretty much. But yeah, it was really cool to see those numbers come through. So then if you want to go to the next slide, Lindsay, it's kind of the conclusion. At least for future work with my data set, this summer I'm going to be working on confirming those numbers and making sure that they were correct. And if they were correct, then we know that those are in fact intermediate mass black holes. But I just want to, we just want to make sure that those numbers are good, and using another method for finding the mass of the black hole, confirm the numbers we got. And so if we do find them to be intermediate mass black holes, that's a really big step towards understanding the evolution of galaxies and the formation of supermassive black holes. And if that doesn't look like it works, or it looks like the numbers aren't working out, that means that there's probably still a gap in our understanding, and we have to find other ways that large galaxies and supermassive black holes form. Sorry, Lindsay, I kind of talked through that. I don't know if you have anything you want to add.
I was just going to add, just in general, we know a lot about galaxies, but there's so much more that we don't know. We don't even know at the beginning of the universe if, galaxies formed first or stars. So this will really help us hopefully figure out also kind of what was there in the beginning of the universe.
And another kind of positive result, should the numbers that I reported be confirmed, is we know not only that those galaxies are intermediate mass black holes, but we know that we have a way easier way to identify intermediate mass black holes, because previous to this pitch angle method that we're using in this project, the best ways to find the mass of a black hole are extremely time intensive. They take a lot of computer work, a lot of just a lot of time, and it's very hard work to estimate those. But if we know that the pitch angle method is a reliable method and it gives good numbers, we know that rather than do all of that very time intensive work and look at different types of light coming from the center of the galaxy and see how fast things are moving around that black hole, we know that we can just look at the structure of a spiral galaxy, see how tight those spiral arms are, and that gives us an estimation for the mass of the black hole. So not only will it confirm that these black holes are intermediate mass, but it'll make it much easier to find more of them going forward.
So I have a question for you guys. And if anyone else has other questions, again, leave them down in the chat. But let me turn my camera back on. Before this work, how many intermediate mass black holes were known?
There's a handful. I mean, like we know that, or according to estimation methods that are used previous to the pitch angle method, there have been a few that have been identified, but not a lot, I don't think.
Yeah, this is kind of on the cutting edge of black holes and galaxies.
Which is why I wanted them to share it, because it's awesome. I mean, if these numbers turn out to be correct and this method reliable, they have significantly increased the data set for the intermediate black holes that we know exist, which is amazing. Sorry, I totally led with that question because I wanted you to brag on yourself, okay? Oh, it's so cool. All right. I also like how this really shows the scientific method and process, right?
Yeah.
Like
Yep.
we have a hypothesis, you've got the data, you've got some numbers, but now as good scientists, we are confirming that
Yeah.
stuff is correct.
Yeah, it
And
was kind of interesting because like planning out the project with the faculty advisor that Lindsay and I are working with, it was like I didn't really think about it that way, but like in hindsight, looking on the project, it was like that's totally how it played out. It's like I think this is happening. Okay, let's get some pictures of galaxies and work with them a little bit. Now we get numbers from the pictures. Are those numbers correct? And it very much is. I'm kind of brought back to 6th grade chemistry, thinking about the scientific method. It's really cool.
I
And it's
mean,
just cool to see it in action.
yeah, it is really how we do things.
Right.
So that's cool. I'm sorry, I'm feeling all like mama bear proud of my little planetarium kids. Uh, all right, let me check. I'm not seeing any more questions at the moment. Or, oh, here we go. We just got one. Are scientists going to create a black hole in a laboratory that destroys the Earth? Lindsay.
No.
Okay, so we get this question actually a lot. So we're talking, it's CERN, right? That might be making the black hole. Okay, so black holes do not actually last forever. There is something called Hawking radiation. And so first of all, the black hole, if we made one at the CERN laboratory, it would be really tiny. And because of Hawking radiation, it would actually evaporate really fast before it could cause anything to happen here on Earth. So
fractions of a fraction of a second.
yeah. So once all of our stars have died and become black holes or become part of black holes, we're going to have this age of the universe that's just black holes.
Yeah.
But again, they don't last forever. So the Hawking radiation is going to slowly make them evaporate, and then there's going to be nothing.
Yeah. And if I can add on a little bit about like black holes and gravity and the interesting thing that it took me a long time to realize, like I realized it last year, and I remember I was at the planetarium when I realized it, and I kind of had like a lightning bolt moment. But the reason like the sun doesn't suck us in the same way a black hole does is because when you're at the surface of the sun, you're a lot further from the center of mass of the sun than you would be like close you could get if it was a black hole. The only reason the gravity is so strong close to a black hole is because you're so much closer to the center of mass. So like something can be, the same mass as a black hole, but you're just going to be so much further from the center of mass that you wouldn't experience any like really devastating gravitational effects. And that's why you can safely be outside of that event horizon, because you're far enough away that you're not going to get pulled in. So I mean, even if they did make an incredibly small black hole, which I feel like I haven't heard much about, but maybe I'm just not in the loop. um as long
I'm
as
gonna
you
be
didn't
honest. I think if they made a black hole, we'd know. They
Yeah,
would
as long as you
say.
didn't like put your finger on it, you'd be fine.
I think it was a huge thing when CERN first started, and I think Jessica and I were a little older when that happened, so we probably noticed it a little bit more.
Yeah, I definitely remember the fear mongering around the startup of CERN.
Yeah.
But that's also, I mean, I want to say one of the reasons we here at the Planetarium, all of us, are so passionate about doing these shows is so that we can help people better understand what's going on and not have that fear of the unknown or fear from not understanding. I mean, that's what we do. That's what we want to be. And so, yeah, I don't know, maybe I went off on a little tangent there.
No.
All right, well, I am not seeing any other questions. So last call, if you do have any last questions, leave them down. I will tell you a little bit about what's coming up over the next week. So on Saturday, we are going to do a fun show for you about this group of objects called the Messier objects. They come in, there's lots of different types of things within this group. Some of them you can even see with your naked eye. Some of them, or most, you need very small telescope or a pair of binoculars. And there are some out this summer that are really awesome to try and take a look at. So we're going to kind of walk you through what these things are and give you some good ones to try and see this summer and fall. Next week, next Wednesday, we are going to do a new show in the works called Astronomy Fact or Fiction. This is another one that Eli has been working on. If you know, Eli's done the revamp of the Star Wars. That's the word. The Star Wars show. So this is another one that we are in development to do in the dome, full dome.
Yeah.
I'm struggling with my words tonight, guys. But we're gonna run a small version of it for you next week. So we're excited about that. And then next Saturday, it's been a while since we've taken a visit to the planets in our solar system, so we're going to do that. We'll hop in our virtual spaceship and go visit all of the planets. All right. Not seeing any other questions, so I think we are good there. So thank you everyone so much for hanging out with us tonight, hearing some of the awesome research. If you liked this and would like for us to do this more often, let me know, because I mean there's lots of cool student research going on at UMD, and I just kind of hit me tonight that like maybe this should be a regular thing we do and highlight some of the student research. I mean, why not? It would be fun. All right, so let us know if you'd like to see more of that, and it doesn't have to just be astronomy. We can get other fields and departments in as well.
A lot of physics research about Lake Superior, actually.
Yeah.
Yes.
Yep.
Yeah, a lot of cool stuff going on there. All right, well, we will close it off there. Thank you again. We are planning on streaming through the summer at our regular times. We don't know quite when that'll stop. It'll be whenever we go back to fully open, which won't be till the end of summer, probably. Anyway, well, I don't have dates yet. I'll get you information, I promise. But okay, I'm just going to stop talking and stop rambling. Thanks for coming. We hope you enjoyed, and we'll see you next time. Bye, everyone.